the formula for cardiac output is equal to heart rate times stroke volume, right? Which chamber of the heart has the largest stroke volume?
The ventricle, the left ventricle.
Which chamber, or which we narrow it down to the ventricles, which ventricle would have the largest stroke volume?
Don't they have the same?
They're equal, they should be.
Yeah.
So that was a kind of a trick question. They would have different pressures, so the left ventricle is going to contract the hardest to push open the aortic semilunars because it has a greater force against that it has to open against compared to the right ventricle. But they should have the same volumes or we end up with congestive heart failure. All right? So thinking back to that diagram of the different pressures, the aortic pressure versus ventricular pressure versus atrial pressure, all right, and combining those two concepts. So this is one stroke, this is one full ventricle of the heart. So they should both have the same volumes. So what do we call the largest volume that a left or a right ventricle would contain? When is that going to happen? When is the heart the most full? The ventricle of the heart the most full?
Preload?
Pardon?
The preload?
Well, not the, yes, but at the end of contractile, so at the end of heart rest, at the end of ventricular filling. So we call that end diastolic volume, yeah. So C here represents end diastolic volume. Diastole means the ventricles are relaxed, okay? The diastolic pressure we'll talk about next week has to do with that. So end diastolic pressure, or end diastolic volume rather, or EDS. And what's the typical average volume in one ventricle for end diastolic volume? Remember? 135, okay? So this total A plus B is 135. So this upper volume here represents what the ventricle is pumping out. So we call that stroke volume. So of the 135 mils, the heart doesn't completely empty it. It's just a little bit over half. And so what's left after the end of ventricular ejection, when the AV valves open again, the semilunar valves close and the AV valves open again, at the end of, just before the AV valves open, we would have then in systolic volume. And so our average here is 70 mils, right? And this would leave about 65 mils in the heart in case you needed more blood. You had to run really fast or jump up and down or run up the stairs or whatever. Your heart can come back with a stronger contraction and give more access to that, okay? So now let's look at some of the conditions that can cause changes in that. So if we look over here, our end diastolic volume is still the same, right? Our top volume here is still 135 mils. But our stroke volume is greater, meaning our end systolic volume is less because our stroke volume is greater. What makes our stroke volume stronger?
Stronger heart.
What to change do we need to make in the ventricular contractile cells?
Contractility.
Contractility. And what is the most common cause of an increase in contractility?
Digitalis.
Non-medical, non-pharmaceutical.
Calcium.
Yeah, it's calcium ions. So more calcium ions are going to increase contractility, okay? Now, what's the neurotransmitter that's going to cause cyclic AMP to open more calcium channels in our ventricular contractile cells? No, acetylcholine doesn't bind, don't get caught on that. Acetylcholine doesn't bind to ventricular contractile cells. So when we talk about acetylcholine, it's going to be the autorhythmic cells only. Okay? So the other, and that's going to slow down heart rate. Norepinephrine will bind to both autorhythmic cells and ventricular contractile cells. So norepinephrine binding to its beta-1 receptor on ventricular contractile cells will cause more calcium to come into the cell from outside, as well as more calcium to leave the sarcoplasmic reticulum. And so with more calcium binding to troponin, just like in skeletal muscle, that moves aside, tropomyosin moves aside, we have more binding sites for myosin. It's like adding more people onto either end of a tug-of-war rope. Okay? So, Barry, you mentioned digitalis. That indirectly increases calcium in the cell. Okay? What is digitalis, what protein channel does it bind to or affect?
Then
The pump, the sodium,
The sodium-potassium pump. Okay, so it's kind of an indirect steps. So digitalis slows down the heart rate, but it also increases contractile force by decreasing the effectiveness of the sodium-potassium pump. So we're not moving sodium out. These are a couple of steps here of a review. We're not moving sodium out, but sodium still comes into the cell via, so we still have sodium leaking into the cell via open leak channels. And normally the sodium-potassium pump would take care of that by pumping the sodium out. Since the sodium-potassium pump isn't doing that as well, it's not going to completely stop, but certainly a few of them are working, then we continue to have sodium leaking into the cell. It's not being moved out. And so the inside of the cell gets more sodium. There's already more outside the cell than there is inside the cell. Okay? And it starts to increase in positivity. What happens to the rate at which sodium is moving into the cell?
It decreases.
It decreases because the differences between the two become less. All right? So as more sodium enters the cell, the differences between the two become less, and so this slows down. Sodium input slows, and as less sodium comes into the cell, our sodium-calcium ion exchanger, with less coming in, we're going to have less of the calcium. Less sodium is going to come in here as well, and therefore less calcium is going to go out. Kind of a series of changes to look at. And so with less calcium going out, we end up with keeping that calcium instead of returning it to the outside. And that because of this, digitalis causes more calcium to be in the cell. So it's kind of a couple of steps. The digitalis itself decreases sodium-potassium pump. That allows sodium, that would be the first step, that allows sodium to build up in the cell. Less sodium diffuses into the cell, so less calcium is exchanged out. And therefore, more calcium stays in the cell, and we have increased calcium. Okay? So that's going to increase contractility. By contractility, we're meaning more myosin binding to actin. Okay? Now, people confuse that with this effect. So notice what our end-diastolic volume is here. It's much greater. So either through exercise or increased blood volume from increased fluids in the body, the heart wall, if it's not weakened, stretches out. We have, that can happen during breathing in when you lower the pressure, but we always have to breathe out again. So usually it's increased exercise activity or increased blood volume in the heart from increased fluids. Because that fills the ventricle up, that stretches the actin and myosin filaments, increases the length of the muscle cell, and therefore it comes back again, it contracts with a stronger force, but only back to its original shape. Look at the level of the stroke volume. Okay? That's not any, there's not any less in systolic volume than there was with a normal in diastolic volume. So that greater force of contraction, that elastic rubber band isn't going to make a smaller diameter, right? It's only going to recoil to its original stretchiness. And so that's what the heart muscle does under Starling's law. It doesn't contract any harder without calcium. It just comes back to its normal muscle length to take care of all this additional volume that is stretching it. So the Frank-Starling law is illustrated by this. And the key thing to look at is we have a normal end systolic volume. Now you can have both, okay? So if you saw this diagram, but with the end systolic volume down here, then you would have both starlings and additional calcium and contractility of being affected. All right? Then this one here, we have the same overall end diastolic volume, but our stroke volume has decreased. And this illustrates afterload. Okay? So there's a greater resistance to blood leaving the left ventricle and going into the aorta. And I illustrated it last night in this pre-quiz discussion. I say, okay, so I have blood in the left ventricle, pressure is increasing, and I'm pushing the door open, semilunar valves open and going into the aorta. Well, let's say that there's, 500-pound person out there that I have to push against to be able to open that door. That's that increased resistance, either because of increased venous pressure, the bearing down like that, which is usually just temporary. It could be due to high diastolic pressure, so when the heart's at rest because of atherosclerosis or some unknown cause of high blood pressure, instead of being 110/70, it might be 120/90. And that 90 means that's the pressure that's in the aorta or the brachial artery when the heart is not trying to push blood in. So instead of pushing against a 70 millimeter pressure, it's having to push against a 90. So that means that that heart muscle is having to do more, and therefore it's not going to be able to, if it's weak, be able to push out quite as much. Okay? Normally, until it gets weakened, it just has to work harder to get to here, and it will do that. But as it gets weaker, it won't be able to do that. Okay? I just wanted to review, so you weren't just going, what am I looking at here? Because you'll see questions like that on the quiz. All right, any other components? Ready? I don't have the drawing for the blood supply to the brain, but that's pretty easy to access. So our quiz on Thursday will stop at the abdomen. Okay? Well, we covered that in lecture today, but I won't include on your lab quiz Thursday identification of the arteries in the pelvis or the arteries in the lower limb. So over here, I have the parts of the aorta, ascending arch of the aorta and thoracic aorta, which is the part of the descending, and then the brachiocephalic trunk, common carotids, and as we move up into the head and neck, we have the external carotid, and the internal carotid stays pretty large as it's going up into the brain, maybe not that much size difference. All right, then we have off of the external carotid, we have the superior thyroid, and the only model, the lab quiz will be a combination of models and diagrams. The only model that I know that we have the superior thyroid on is this one right here, and there. And you can see the superior thyroid coming right down to the thyroid. Okay, you can't see it coming off the external carotid, but you can see it coming to the thyroid. So as much as possible, I like to quiz you on not just like the wires in the back, wires sticking out in space, but you'll notice that many of the names of these vessels are for the organ or the region that they're going to, okay? So lingual is going to go to the tongue. Facial, you can see on, and lingual, I don't know that we have a good model for, that might have to be a diagram. But facial is the really curvy one that comes across just under the skin and kind of goes up the side of the nose. You can also see occipital on here. And then the terminal branches of external carotid are the superficial temporal. There's multiple branches of that. The maxillary artery with the middle meningeal is this horizontal one here. It's also a branch of external carotid. And it sends off a small little vessel that pierces the floor of the skull and supplies the meninges from within. So when I'm teaching 430, I tell my students the temporal squamous portion of the temporal bone is the thinnest portion of the skull. And when that's broken, baseball or fist or piece of wood or whatever, that can tear branches of the middle meningeal. All the little grooves that you see in the bone are from branches of that. So right under here is the maxillary artery. And if you look inside, you'll see these pair of small little arteries tracing up against the bone. Those are not part of the cerebral circuit. That's the middle meningeal. It doesn't supply the brain, it supplies the inside of the skull and the meninges, like the dura mater and rhabdoid mater. Okay? So then we have the internal carotid, and on here you can see the internal carotid coming up through the carotid canal. I don't have a diagram of the cerebral circuit, but you can also see the vertebral arteries coming up through the transverse foramina of the vertebra, and see there where they join together to form the, they come up, two vertebrals come up to form the basilar, and then form the posterior cerebral coming back here, and then with the internal carotid we have anterior cerebral and anterior communicating. The artery there's two arteries that supply the cerebellum, posterior inferior cerebellar off of vertebral and posterior cerebral. So the posterior inferior cerebellar can be seen, where's the model? Right here. So on this one, it doesn't go past the posterior cerebrals, but you can see coming off of the vertebrals down in the foramen magnum, you can see these two branches, which are the pica or posterior inferior cerebellar. Okay. Then, so those are all of these branches, and then off of the brachiocephalic trunk, we don't have it on the left side. The very first branch is that vertebral one that I just showed you, and then we have the thyrocervical trunk. This is going to be on a diagram, okay, because our torso models don't show that much past the skin. There's multiple branches. I just want you to know two. One is the inferior thyroid. That will be from the diagram. So it's going to go to the thyroid gland. If it's not coming down from the top, it's the inferior thyroid. Suprascapular, I don't know if you remember the suprascapular notch from the scapula, right there just above the spine. This artery goes over the shoulder to supply the muscles of your scapula on the back. Okay. Then over here, I'm doing the anterior and posterior chest wall. So off of the thoracic aorta, we have the posterior intercostals. And you can see those on the wire circulatory tree in the back. I hesitate to bring this down, but it is good for certain structures. What I said a few minutes ago applies. I don't want you having to memorize wires just sticking out in space. So this is good for chest. Here would be the internal thoracic with anterior intercostals. Here are the posterior intercostals coming off the back of the aorta, all right? It's good for upper limb and lower limb, especially the veins, because those are hard to find on other models, and the veins of the posterior chest. Please don't try to memorize all this bird's nest of wires right here. Okay, I'd rather you see that with our organ models where you can see the organs that they go to. Okay, but I do use this for the upper and lower limbs and for these arteries of the chest wall, draining and the veins of the chest wall. Okay. So, in addition to the posterior intercostals going posterior, we have these two arteries in the front, which are the bronchial arteries. People tend to forget about those, but the lung needs its own oxygen supply. So the pulmonary veins are not carrying oxygenated blood to the lungs, they're carrying oxygenated blood to the heart. The pulmonary arteries are carrying deoxygenated blood to the lungs, so that's not going to provide oxygen and nutrients for our smooth muscle and cartilage and all the other tissues of the lung, and that's what the bronchial arteries do. Okay? So they go into the lungs with the pulmonary veins, arteries and veins. All right, then here's the internal thoracic, and that wire model that I showed you is good for internal thoracic and the anterior intercostals. The other location to see the anterior intercostals and internal thoracic is this chest wall right here. So on the deep surface, you can see on one side the internal thoracic artery and veins. And then coming off of those would be the anterior intercostal vessel, which join with the posterior and just become one vessel from front to back. Okay. Then for the upper limb, it's pretty basic. probably the easiest of the set of vessels to learn because we're so familiar with those bones already. So the subclavian becomes axillary after it passes under the clavicle, becomes brachial after it passes by teres major, and it's brachial until just above the elbow. When we take our blood pressures, next week we'll be using brachial. The artery to the posterior arm is the deep brachial. And then to the thumb we have radial, to the little finger we have ulnar. And the ulnar, we have 2 arches, although that wire model shows 3. The superficial arch comes closer to the fingers, and the deep palmar arch is closer to the wrist. So most of the superficial palmar arch gets blood from ulnar. Most of the deep palmar arch gets blood from the radial. Okay, pretty basic. And then this is where we stop, or the lab quiz is the lumbar vessels. So all past the aorta, everything past the diaphragm, everything is abdominal aorta. We have vessels going to the lower part, inferior part of the diaphragm, so that's inferior phrenic. And you can see them, I think, on that model in the back of the room, the upright reddish brown one. And then we have the celiac trunk. So we have 2 trunks here. Typically they're called a trunk when they don't supply blood to any particular location. Branches of them do, like our pulmonary trunk. And then we have the 2 pulmonary artery branches. So the celiac trunk is off 3 vessels going to the spleen, splenic, going to the stomach, gastric. This one's called left gastric. We have another one we'll learn at the end of the semester called the right gastric. That finishes us off, but it's not a branch of celiac. Going to the liver, we have hepatic. All right, and the best view for those vessels is kind of have everything head here and everything abdominal here. We used to have an old antique model that really showed the stomach vessels well, but under here, tilted under, you can see celiac trunk and the branches for left gastric, celiac, splenic, and going over to the spleen, and then going over to the liver is hepatic. All right. Yeah, inferior phrenic is shown right here on this one right here. Now I have quite a bit of distance between my diaphragm and the adrenal gland. It's only about 2 or 3 inches. I just kind of stretched everything out so it wouldn't look quite so crowded on the board. All right. Now you'll notice that superior mesenteric is headed over to the right, and that's because it supplies all of the small intestine. You notice the name mesentery? So that's a double layer of peritoneum. You see right here, it's peritoneum. And so it supplies all of the small intestine. And then it's going over to the right because it also supplies the ascending colon and the transverse colon. So superior mesenteric is going to go over to the right, that's this vessel right here. And then we have inferior mesenteric, and you notice I have it going over to the left because it's going to do descending colon. So here's inferior mesenteric, left colic, left colon, and then coming down to the top of the rectum. Top of the rectum is superior rectal artery. Okay, so use those types of class names because they're really naming the organ or the region that they're going to. So here would be inferior mesenteric, left colic, and superior rectal. Then we have the renal, pretty obvious, going to the kidneys, and they're really large. And sitting on top of the kidneys, we know are the adrenal glands or suprarenal. They are endocrine organs. They get 3, like the thyroid got a superior and inferior. These get superior, middle, and inferior. So I draw this really long. It's really only about a third that long. We have superior adrenal coming from the inferior phrenic, middle adrenal coming from the aorta, and inferior phrenic coming from the renal artery. Okay, you can see superior phrenic, and one of our models back there has inferior, but I need a diagram for middle. Then we have a pair of gonadal. They're very small, about this little bit bigger than the size of lead in a pencil. So whether they're ovarian or testicular, we don't know the gender of this person, so gonadal. And then we have the lumbar, which are really a continuation of the intercostals, but they're not passing between ribs, so we just call them lumbar. And you can see those on the wire models as well as the posterior intercostals. Okay? So the quiz on Thursday will come from those as well. There will be one question on identifying a particular blood vessel. So a capillary, an arterial, which just has 2 layers of smooth muscle, all right, an artery, or a vein. Okay, so for the ABCD quiz
That would
question.
be like the histology.
Yeah. So just review the images from lecture, the PowerPoints. And just a heads up, if you look at it online, a lot of vessels that have 3 or 4 or 5 layers of smooth muscle are called arterioles, and that's not correct. Those would just be small arteries. So it has to have only 1 or 2 cells that are smooth muscle cells. Okay? All right. So